So we will continue with the second part of the session on methods and measurements. So the next speaker is Howard Dieter. He's Vice President at Jonah Energy. He will present a study on reconciliation of the inventories with the site level measurements in line with the OGMP 2.0 framework. So Howard, the floor is yours.
Can you guys hear me okay? All right, well, good afternoon, and I'm Howard Dieter, Vice President, Environmental Health and Safety with Jonah Energy. Jonah is the first U.S. company to sign on to the UNEP Oil and Gas Methane Partnership regulations very proudly, and we're representing the United States here. We wanted to give you some information on our first attempts at quantification and reconciliation of a variety of emission sources. So, as I said, we were the first company to sign on to OGMP 2.0. We're an independent natural gas producer in Wyoming. Our headquarters are in Denver, Colorado. And we also are a member of a trade organization called One Future. It's a U.S.-based voluntary trade organization that represents about 40% of the natural gas value chain in the United States. And One Future is making significant progress towards adopting a quantification-based approach to methane emissions reporting. We and some of our colleagues are pushing that organization to move in that direction since we represent such a large part of the value chain. So obviously we all know what the challenge is. It's been enumerated from European Commission. It's been enumerated from the administration in the United States. We need to create transparency. We need to have a good methane and carbon intensity reporting protocol. And from Jonah's perspective, that means adopting OGMP 2.0. We know that it's a robust measurement, reporting, and verification standard. It is gaining momentum both internationally and nationally within the United States. It is asset-based, and so it does not cherry-pick or segment individual wells within a production facility. So it is a comprehensive view of a company's emissions across their entire asset. In the U.S., we report on basin-wide basis to the Environmental Protection Agency. And so OGMP covers our entire reporting within that basin. And ultimately, it drives emission reductions. You've seen a lot of presentations about how well different types of technologies quantify emissions. The really next important step beyond that, once you have that, is to understand materiality and then where you deploy capital to reduce emissions in the grand scheme of things. So our view of the multi-scale measurement process are these various layers to achieve a level 4. So beginning with a comprehensive emission inventory. And in the U.S., our EPA Subpart W reporting is not a comprehensive emission inventory. It represents some aspects of emissions, but it isn't necessarily all of your emissions, and it certainly isn't necessarily all of your material emissions. So in order to inform that, we're adopting a number of other parts of data and information. One is operational data through our SCADA system, our SIGNET system. So understanding what is happening in the field and coordinating that operational data with other things that are going on. We're also using site level and source level measurement efforts through drones, through high flow samplers, other types of technologies like stack testing our engines. And those measurements of those emission sources now begin to even better inform your comprehensive emission inventory, which is going to ultimately make the reconciliation of that with a top-down measurement that much more comprehensive. And then we'll get into a little bit of the basin-wide measurements that we made here in the first quarter of 22. And they are our mass flux. But we also looked at quantification of non-operated contributions within that mass flux and looking at other types of non-production related emissions emissions that don't happen on a day in and day out basis from our operations, like a workover rig on a well that needs help. And we're looking at how those emissions then add into the production emissions that we have on a basin-wide basis. The technologies that we're using right now, we've looked at a number of different technologies, but we used a manned aircraft with Scientific Aviation. Their Mooney aircraft that you saw in a couple presentations. They conducted raster flights and basin-wide flux flights. We're looking at site-level quantification using a drone and a methane sensor, as well as air-level LiDAR through Bridger Photonics. And then the bottom up, as I said, we're looking at quantification efforts of different sources. We're looking at high-flow samplers through our LDAR program, our leak detection and repair program, and then looking at an engineering simulation called MEET, which stands for Methane Emissions Estimation Tool. It's an open-source tool that was developed by the University of Texas and other researchers. That begins to give us a broad idea of what each individual facility's emissions look like on a temporal basis against which we compare our measurements. We looked at how we characterize our facilities to come up with statistically representative samples. We think there's 5 or 6 different contributions into our production level measurements listed on the left, and then a few of the intermittent kind of non-production sources that we're looking at on the right-hand side. So this study is really looking at one specific emission source. I don't have time to go into all the ones that we've looked at. But this specific emission source is liquids unloading when a well has enough fluids into it that it cannot produce. We're predominantly natural gas, and so those fluids tend to restrict gas production, especially in older parts of our field where we don't have enough reservoir pressure for the wells to produce. All of our wells are on plunger lift, and so the plungers actually help reduce the instances of liquids unloading through this process. But what I want to walk through is the value of level 3, level 4, level 5, and how it really relates to the emissions for this particular source for us. So under the EPA and other emission factors that have been developed, the first option we would have would be to look at a per well basis. And data that's been published by Dr. Allen at the University of Texas indicates 117,000 standard cubic feet per well per year. So if we apply that to just the number of wells, we end up with about 3,315 cubic meters of emissions for that well. If we then take the next step of actually looking at the number of times that we conduct a liquid unloading on our wells, the emission factor is actually 9,800 standard cubic feet per event. And you can see the difference by just tracking the number of events instead of attaching it to the number of wells. You end up with about a third of the emissions just by looking at the number of events. So we view this primarily as some activity factors, but primarily a level 3 effort where we're using an emission factor, but also using some events that we use. Then if we look at, in the blue, what actually happens on each event. So a volume of gas that gets vented in the tubing, what is the depth of the well, what is the well pressure, temperatures, and duration of the blowdown event. We begin to then input those activity factors, more detailed activity factors, into an equation, and we actually come up with a significantly lower cubic meter per well using that calculation. And that's an EPA calculation, and the question is, how accurate really is that? So these are generally OGMP level 3, level 4 activity factors that we're collecting for each one of these events. And you can see the difference from 1,200 to 280, so it's a factor of 4 lower than just using an event-based quantification method. And so we wanted to see how accurate each one of these different measurements were, and we had an opportunity in April to go out and actually measure using manned aircraft with Scientific Aviation what the quantity of emissions were from 2 different types of blowdown or liquid unloading processes. One of the key parts of this is we share our data with our operations team, and we tell them what we're seeing from an emission standpoint. And we ask them to go out and say, how can you change operations to make this a little bit better? And so the first measurement on the 27th was done comparing a better liquid unloading process. And the second measurement on the 29th was how we generally do this. So we have one of our production coordinators that really takes a look at this and says, I can do this better. And you can see the differences. And the first measurement on the 27th definitely shows that that is much more in line with the collection of activity factors, well volumes that you're blowing down, and so forth, than the measurement that we made on the 29th. And so we think that we're honing in now on what is the right process to do a liquid unloading and making sure that all of the calculations that we're making through the equation, the well volume, duration, pressure, temperature, et cetera, are going to more accurately represent what we're doing, and then we can take that local site level emission factor and apply it to all the events that are occurring in the field. We think that those, because it's the number of liquids unloadings that we do on a daily basis, we think that the raster flights are picking that up as part of the background emissions. They're either going to be seeing an event or they're going to be seeing the plume resulting from an event. And so the more often we can conduct raster flights, the tighter that we can get those flight measurements, the better it's going to be for us to include those liquids unloadings within our overall basin-wide flux. There's a couple other examples I won't go into details on, but we saw some earlier presentations on drone-based measurements, and this is a picture of a drone-based measurement that we were doing in April, looking at a collection of emission sources at our production facility, looking at the emissions associated with those sources, and we'll be doing some additional quantification work. We don't have all the data back on that at this point, but this will be work we're doing here in 2022. This was a workover rig that we were going onto a well that needed some help. And so we were looking at what would EPA say, and they give us an emission factor of 0.54 metric tons of methane per workover. But when we actually did the flight quantification using the manned aircraft and Picarro sensor, we were getting a much higher kilograms per hour rate from that workover rig. So then we could take the workover report that our operations team put together, look at how long and what the duration of that emission rate was for that event. And you can see that if you expand that emission factor we got for that event over 78 workovers that we did in 2021, it's a factor of 8 higher. And so we're going to be taking that data and using it then to, again, better inform the additive values into our overall flux reconciliation. Another example, we stack tested all of our engines in 2021, and we actually created methane quantification from them. And you can see the difference between a standard EPA emission factor per engine and what the stack testing actually showed. And so our year one report into OGMP now includes another 800 metric tons that wasn't included in the original emission factors that we put in. The next slide really gives you a better idea of understanding materiality associated with these different measurements. So you can see on the left if you're just doing an emission factor distribution, and on the right if you're doing quantification. And so when you think about deploying capital to reduce emissions, it's really important in our view to understand the materiality of the different sources. Otherwise, you could be spending a lot of time on gas-actuated pneumatic pumps when it really doesn't have the contribution, because we already collect the emissions from the exhaust off of those pumps and put them into a combustor. And so really, every operator, every basin is going to be different on what that answer is, but the materiality is really an important part because it really drives limited capital for all of our companies, and we're a very small company. So we're about 0.5% of daily production in the U.S., so relatively small. We also did some basin-wide flux measurements, and these are 2 examples of the data we got from that. Those basin-wide flux include our emissions and also some other non-operated contributory emissions. We were able to isolate those. We were able to isolate those with individual flights and understand what the contribution of those non-operated sources are. They're compressors that compress our gas once it's been sold, and they're operated by 3 companies that are within the basin, not Jonah. And then ultimately, when we're looking at thinking about how the reconciliation is going to work, Uh-oh. There it is. So what we're thinking about is when we submit a number to OGMP, we think about all the adds and deductions from that number and comparing that against the basin-wide flux. And if you look at the flux compared to our year one report in OGMP, it's about 20% difference. But there's some uncertainty that's obviously captured within that. There's some things that we know we need to add. There's some things that were in our year one report that don't happen all the time. And so this is just how we're viewing that reconciliation approach. So this is a gap analysis of the things that we learned along the way. There are a number of questions as we go through this process, and I think every operator will go through the same sets of questions. But how, what other measurements do you need? How many of those measurements do you need to take? Getting more basin-wide flux measurements. Obviously, one isn't statistically representative, so we're going to need to do that. And then developing other technologies to look at longer-term source patterns, like a drill rig is very hard to get with just a drone or just a flyover. So can you use an OGI-based camera? And we're testing some of that technology right now to get a longer duration emission from those types of sources. And that's it. Thank you very much. I appreciate the opportunity. Thanks, Tanya.
So thank you very much, Howard. It's very impressive to see all the efforts that Jonah Energy is doing. So our next speaker is Thomas Röckmann. He's professor at Utrecht University, and he will be presenting the results of the gas ROMEO measurement campaign performed in Romania. Okay, Thomas?
Yes. Thanks a lot, Tanya, for the introduction, and Rod for the invitation. I'll take you back from the industry back to science. I work at Utrecht University, and I'm presenting the project with arguably the nicest acronym, the ROMEO Project, Romanian Methane Emissions from Oil and Gas, which we did together with a large group of people. Here you see again, maybe also the most famous aircraft today, the Mooney aircraft of scientific aviation. It's probably the most photographed in this meeting so far. Mackenzie is also here, who joined us in the campaign. And there are many other people, which I didn't put all the names on here, and it's also only half of the people. So there were a big group of scientists and in Romania for this measurement campaign. Let's see whether this works. Yes. I will first give you a short rationale why we went to Romania to do these measurements. Then I will give a short campaign overview. I will talk about the methods that we employed and then show you some results. So why did we go to Romania? Of course, as we heard this morning, the EU publishes emission numbers, and when we were planning this study, we had the emission numbers here from 2013, and here you see the by country reported emissions in Europe at that time, and Romania was the region with the highest reported emissions. If you then ask how many measurements have been carried out there, it's actually, well, we have just seen a very active operator, but there are almost no measurements done in Romania. So this is all based on reporting, and they may be high, they may be low. We don't really know unless we go and carry out measurements there. They have a relatively large onshore oil and gas reservoirs. So in principle, you should say, well, there's high production, there's probably also high emissions, but we should actually go there and find out what the emissions are like. We went with a rather large team. It was part of a Marie Curie training network that was financed by the EU. We got additional funding from UNEP, the Climate Clean Air Coalition, and EDF was also involved. We had then, with all our European partners here from the UK, France, Germany, Netherlands, Denmark, Sweden, Poland, Switzerland, we all went to Romania and carried out measurements together with a couple of Romanian partners, especially our host institute, INCAS. But then we also had links to the ministries of the environment, of energy. We had two energy operators on board, OMV Petrom and Romgas. And then we also had a company that's here, the sniffers and the scientific aviation that came with the aircraft. So it was quite a big effort in terms of this CCAC project. It was certainly one of the bigger ones. Oh, that was one too fast. We first got information from one of our Romanian partners about the oil and gas reservoirs, and here you see Romania, and the red oil and gas reservoirs here, they are the ones which are operated by OMV Petrom. The green ones here in the Transylvanian Basin, they are operated by Romgas, and the blue ones are all other operators. So these two that we have in the team are really also the main operators in Romania. In this talk, I will focus on the measurements here in the southern part of Romania and the second phase of the ROMEO project, which is now evaluated by the University in Krakow. That will be, well, I will not cover that here. We did certain types of measurements. We did component types of measurement with optical gas imagery and the high flow samplers that to find really leaks on individual components. We did the site level measurements where we often drove past plumes and either with or without additional tracer release, sometimes also not mobile but standing in the plume, the so-called OGM33A method. This is for facility type quantification. And then we also had, with the aircraft, we had basin type quantification where we had made these box flies that you have seen also a lot today, but which I will also not cover in this presentation. I will mostly focus here on the facility and partly also the component style measurements. Then we come to the results. I will present the results first on the component and site level. So we had a team from the sniffers in Romania. They went with the OGI camera and we sent them on different days to different regions and said, well, examine some of the wells there, of also larger facilities. And they visited in total 181 sites here. 155 of them were oil wells. And they also record the images and the videos. My student has also now, is she here, Fortini? She has really watched all these movies and made statistics of that. And when you just look at that, well, the most simple statistic is that 50% of the facilities that they visited had leaks, visible with the OGI camera, and 50% did not have leaks. From our mobile teams that went with the other quantification methods, we know that we see that the leak rate is actually even higher. I will come to that in a minute. When we then look at all these videos and try to identify what are the leaks of these 155 oil wells, the numbers don't add up here, sorry for that, but you see that a very large fraction of leaks is an open end at the installation, which is, of course, well, we can talk about rocket science here, but these are really simply vents that are at individual oil wells that are not closed. And some of the people that did the measurement said, yeah, there is a pressure gauge missing here or a valve missing here. It's simply not there. And then there's another large fraction that is coming from below the ground, and we assume that maybe these are also some open ends down there. And compared to this number here, the real technical things that can be fixed, like flanges or threaded connections or valves, are actually in the minority. So we conclude that simply based on these data, the emissions in this area are really mostly due to the design or the state of the facility or the operational procedures when valves are simply not closed. That's also what we saw sometimes. Another point is that we saw, well, this is the southern part of Romania, is mostly an oil production region, but there was almost zero flares. So we never saw it, which means that's simply no flaring happening there. It's very easy to spot this. I told you that this 50-50 spread between emitting and non-emitting sites was even on the low side. And we have a nice proof of concept here that the operators can actually do better, because there was one part of the region that was associated with H2S emissions. H2S is dangerous, so the operators do their best to keep the emissions low. And when you now compare this certain cluster here where we have the H2S emissions, you see that the emitters are much lower. The emitting fraction here, the leaking fraction is much lower than the non-leaking fraction compared to other clusters. So these are production clusters with many wells in a rather small region. And this one, even only part of this cluster was the H2S region. So that is actually a proof of concept that if these operators actually do it properly, they can reduce emissions quite easily. And so in this cluster, we had 25 emissions with 25% of the facilities with leaks, and in other clusters it was. Where am I? Yeah, and so this was low, and in other clusters it's much higher, and that then also agrees with what we found with the other vehicles. And also we found, in this region, we found obviously no open vents, so they never actually let the gas simply out because it's dangerous. How does it look? Who spots the leak on this movie? Well, when you know it, you can probably already guess it. This is the FLIR camera. You see there is an open end here, and when it now changes to the infrared mode, you will see that there is simply a plume. It takes some time of methane coming out of it. Here you see the plume of methane coming out of this vent. You don't need to be a PhD or professor to fix this. So that is also relatively easy to find and to improve the emissions. So this part of the infrastructure there, we saw that the infrastructure has really a very variable maintenance state. So we mostly analyzed oil infrastructure, but we also had some gas facilities, and also at the gas wells, well, we see generally lower emissions, but also sometimes and again because of improperly handled equipment, that means and not properly closed valves or vents, we also saw high emissions there. And it was again less often leaking equipment. Yeah. Then we sent the LDAR team also to a compressor station, and to two compressor stations, and they found in one of them they found 58 leaks, and in another one they found 27 leaks, and they were mostly now on technical equipment here like flanges and valves, and they came back the next day, and together with the local team they fixed 31 of them in a single day, so they already reduced emissions relatively easily. Again, not rocket science, but really it means that if you don't go there, you don't see it and you cannot fix it. And if the people also don't have the equipment to find it out, a simple camera, they can also not really make a progress there. Right. We have also the storage facilities. Let's assume they fix everything at the wells, right? They collect everything, they bring it to the facilities, everything is fine at the well. We find no leaks there anymore. But then they go into these tanks. And these tanks, well, very often, there will be also, should be a movie here. Oh yeah, these are storage facilities below here. There's another one over there. And sometimes they looked at that, you can already see that maybe there will be leaking here where we have these rusty parts. You will see it later. Yeah, so there's a leak up here. And we have this open pipe. Yeah, you only see it later in the flickering image. There's simply a vent here, right? So even if they fix all the leaks, if the infrastructure that follows up on that doesn't really take care of it, it will still be released. And we talked, Stefan and myself, we actually talked to an operator and said, yeah, we used to have a flare, we used to have a compressor, they don't work anymore. Now, once a day we went and let the methane go out to the atmosphere. So this is another story compared to the operator talk that we had here before. We are also doing, of course, emission quantification, as we know on all production basins worldwide, the range of emissions is really high, from really negligible emissions that we can only measure with the tracer release method to something which is of the order of 300 kilograms per hour, which is also not a super emitter, but it's quite a big emitter in Romania. And what you also see is that the cumulative emission distribution always shows this really very small fraction of the sites. 10% of the sites are responsible for 70% of the emissions. So if we are able to reduce these emissions, we're already pretty close to the global methane pledge that we want to do, if you really only focus on these big emitters here. What we also found, that there is not a clear relation to the production, the fossil fuel production, that also has been shown repeatedly. But what we found interesting, so we got all the numbers from the operator, and 52% of the sites report no production, so zero gas production at the old sites. Is that realistic? Well, we think that there is always a bit gas associated with the oil. So maybe not reporting means it's simply not collected. Maybe this is the open vents. Yeah, when you vent it out, it will never actually reach a meter where it can be metered and reported. So we did also these different techniques. We have drones here. You have heard about this. We have this OGM33A method, and we have the tracer dispersion methods here. And we now, well, we are struggling already for weeks and months to come to really statistically robust conclusion of this study, because it is hard. Now I show you only the good part of the story. If you really take really carefully evaluated studies and only the ones where we are sure that they work, we get for all these different distributions here something that passes a test for a log normal distribution. Yeah, see, there's a logarithm of the emission rate here, so we can put a normal distribution to this logarithmic distribution of emission rates. They all pass the test, so it's an appropriate model. And if you then put them all together, this is what the different techniques show. And this is maybe too good to be true. We have already had some contact, especially with the tracer release team, which published a paper previously that included more data, but they were not properly tracer release data. But in this case, I would say this is an enormously good agreement. We were there really in very difficult conditions. The wind speeds were usually 1 or 2 meters per second, and you have seen in Ankerstock how bad these plumes behave in these conditions. But it actually looks quite good. And what do you want to do further? Of course, I could give you the number already, but we still want to be sure before we actually give a number out here. But we want to derive a final representative emission factor for the Romanian gas production in the southern part. We want then, of course, easy to make an upscaling to the national scale. We also have the aircraft evaluations that we want to compare to what we find on the ground for the individual facilities. And then we also want to compare to the inventories and the reported emissions. And I already told you, I looked at the EU reports, and it's really written in the EU that the largest savings in methane emissions have been made in Romania. And you see sometimes from one year to the next a 40% reduction. When I also scratch my head and think, how realistic is this? But we will have a look at that and also come back, hopefully, with an emission factor that is also interesting also for making mitigation plans and so on. And with that, I'm at the end of my talk, and I thank you for the attention.
So our next speaker is Erin Toulos. She is collaborating with OGMP 2.0 and today representing scientific aviation. So she will be presenting the case studies on multi-scale measurements in North America in some oil and gas production facilities. So Erin, the floor is yours. Welcome.
Hi, good afternoon. Thank you. I'm actually going to pass the mic over to Collete Schissel. She's a Ph.D. candidate at the University of Texas at Austin, working on multi-scale measurements and reconciling them together as the topic of her dissertation.
Hi, thank you. Can you hear me okay? So today I'll be presenting on multi-scale measurements of methane emissions in North American oil and gas producing regions. So one of the key characteristics of methane emissions, especially in the United States, is that there is a large amount of temporal variability. And so here's a snapshot visual of the Barnett Shale that was simulated using the MEAT model. And unfortunately, I don't think I can get the simulation to work, but this is at an hourly rate. And what this shows is that there is a huge amount of temporal variability on the hourly scale where sources pop up that weren't there previously. And the range of the magnitude is also really variable. So you might have a large emission pop up that has a really high emission rate, and then it could be gone the next hour. And so what this temporal variability does is it makes short duration measurements really complicated to interpret, especially when trying to reconcile that with annual emission rates. Because these short duration kind of snapshot measurements are really hard to know how they play into annual emission rates without knowing the context of how long they're persisting for, and whether you happen to be measuring at a particularly high emission event or a lower emission event. So I'm going to be presenting on 2 different case studies that looks at this complicated issue of trying to use short duration measurements to interpret intermittent emissions, and also discussing some of the different measurement technologies that we used. So to kind of give a little bit of more context on the measurement technologies, we can kind of think of it in 2 different classes. So there are measurement technologies that are capable of covering large swaths of land, like aircraft or satellite technologies, which in turn, because they can measure a large number of sites in a relatively short amount of time, they have pretty low costs per site. Whereas on the other end of the axis, we have things that really measure at the site level, like a continuous monitoring sensor. And the other kind of variable that can distinguish measurement technologies is how quickly they're able to determine leaks or anomalous emissions. So if you have an aircraft campaign that occurs a few times per year, if you have an emission event, you may go a while before you're able to detect that. Whereas on the other end of the spectrum, if you have a monitor at that site that's collecting continuous data, you would know in near real time if you have an enhancement in your methane emission. And so for the first case study that I'm going to present, we looked at this kind of bottom half. So we looked at drones and a tracer measurement on a vehicle-based measurement device. And this was a case study that was done in East Texas. And so what we did was we measured 33 sites over the course of 3 weeks. And this scatter plot here shows what the drone measured. So we used a CCOPS drone versus what the downwind tracer measurement measured. And so the dots here correspond to a specific site. And so you can see that if the drone and the tracer were measuring the same emission rate at a site level, it should fall along the 1-to-1 line. But on a site level, there's pretty poor agreement between these 2 different measurement mechanisms. And that's likely due to the large temporal variability of these emissions because they weren't measured at the same moment in time. They were measured over the same 3-week span, but they could have been a few days apart. And because of that high level of intermittency, this kind of poor agreement is likely explained because of this temporal variability. But interestingly, when we look at it on a distribution level, so on the right here is the cumulative distribution of emissions, and the 2 different colored lines indicate the 2 different types of measurements, and there's really good agreement when we consider it as a distribution rather than a site-by-site comparison. And so we also looked at a case study in the Permian Basin, which is a high oil producing region, and so it has slightly more complex sites, and we looked at over 100 plus tank batteries and compared that to drone measurements and various different types of airborne measurements. And so I'll go over some of the different aircraft technologies that we used and kind of quickly describe the data products that come with these. So first we use CCOPS as the drone, and so CCOPS uses an open cavity laser spectrometer and GPS and wind data to quantify methane rates. And so this shows the flight path in green, and so it detects the source and then flies in a vertical raster, both upwind and downwind of the source, and uses that to quantify the emission rate. And then it provides a heat map of where the source of the emissions likely is. The next technology that we looked at was Bridger Photonics, which uses LiDAR to measure the path-integrated methane concentration. And you can see the image that comes from the Bridger Photonics technology. We also use scientific aviation, which has been mentioned before. But scientific aviation has a Picaro, so it performs in situ methane measurements, and it flies in a spiral pattern so that it transects both the upwind and downwind concentrations and flies in a vertical cylinder to try to get the entire height of the plume. And it uses those concentrations as well as wind data to conduct a mass balance and determine the rate of methane emissions coming from the source or coming from within the area that it measured. And we also looked at Kairos, which uses reflected sunlight absorption spectroscopy and also takes optical gas imaging of the plume, which is shown here. So we compared, again, the distribution of these different technologies. And so this shows on the x-axis here the estimated emission rate or the measured emission rate. And the small emissions are all the way on the right there, and the higher emissions are here. And then the fraction of the emissions observed. And so, again, there's relatively good agreement when you look at it on a distributional basis, especially on the side of the smaller emissions where there's more data points collected as well. And on a site-by-site level, again, in the Permian, there's relatively poor agreement. And so the y-axis here shows scientific aviation's measurements, and the x-axis shows those measured by Bridger Photonics. And what's interesting here is that a lot of the disagreement comes from non-detections by one of the technologies. And so everything on the y-axis here was measured by scientific aviation, but was not detected by Bridger. And same with on the x-axis, that was detected by Bridger, but not scientific aviation. And likely the reason for these discrepancies is not because the technologies missed it, but because the emission source stopped emitting because they were taken a few days apart. And so again, this is likely due to the large amount of temporal variability. And actually, in this case, when both technologies did detect an emission rate, which is shown in the light blue here, there is pretty good agreement between what both of those technologies are measuring. So when sites continued to persist and emit, there was relatively good agreement between different the measurement technologies. And so just to kind of summarize these two case studies, on a distributional basis, there is pretty good agreement between different measurement technologies, even across different production regions. So for the East Texas case study, which had a low-producing dry gas region, there was poor agreement on a site-by-site level, and it would be really complicated and difficult to try to reconcile it on that basis. But when we look at the distribution of emissions, both technologies delivered a similar cumulative distribution. And we saw the same thing in the Permian Basin, which is a high-producing oil region. That site-by-site comparison was really difficult to interpret because of the temporal variability, but there's good agreement when you look at it on a distributional basis. And so this result kind of begins to ask the question of how many measurements do you need to take in order to get a reproducible distribution? And so to try to answer this question, we did a simulation-based case study in the Barnett Shale. And so I used the methane emission estimation tool, which provides really fine spatio-temporal resolution methane emission estimates for 50 prototypical sites in the Barnett Shale. And I also simulated one of the characteristics of Barnett Shale emissions, which is that there are these high emission events that are relatively rare. They are only occurring about 1% of the time, but they're important for emission inventories because they account for about 50% of emissions. And so we accounted for that behavior, and we varied the duration at which these events occurred. So we varied it from 6 months down to a day, maintaining consistent that they were occurring 1% of the time. And then we took that time series and sampled it annually, semi-annually, quarterly, and monthly to see what the inherent uncertainty is when you try to take short duration samples of a really intermittent data source. And this was assuming no measurement uncertainty. It was just the uncertainty that gets introduced when you take snapshot measurements of something that's really variable. And what we found was that the duration that we selected for these high emission events actually impacted the percent error that we found based on different sampling frequencies. And so as expected, the error increased as you sampled less frequently, but we also found an impact on the duration of these high emission events as well. And so what this case study demonstrates is that the inherent uncertainty due to intermittent and short duration sampling really depends on the behavior of the region. And so when designing measurement methods, you need to consider what the characteristics of a given region are specifically, and likely a measurement methodology that's suitable for one region can't directly be transferred to another region, because even within the Barnett Shale, depending on how we define the duration of these high emission events, there are differences in the outputs that we found. So just to kind of quickly summarize the findings from these different case studies, There is significant short-term variability in emissions from production regions in the United States, and that's really important to consider when trying to interpret these snapshot measurements. But there is reproducibility from these short duration measurements if we consider an ensemble of measurements or an ensemble of sites and look at it as a distribution rather than trying to match on a site-by-site level. And we saw that across different regions, so both in East Texas and the Permian. And depending on how you want to define that ensemble to get a reproducible distribution will depend on the temporal behavior of emissions themselves. And so we demonstrated a case study that we ran for the Barnett Shale, and something similar of that analysis could be conducted for other regions depending on what the temporal characteristics are of your basin. But depending on what those emissions look like, that will inform how you select your ensemble. So that was all I had prepared. Thank you.
Okay, so our next speaker is Jasmin Cooper. So she's research associate at the Sustainable Gas Institute of the Imperial College of London. And she will present the results of the project on methane emissions from global gas supply chains and the assessment of the national inventory reports. Okay, Jasmin, welcome.
Thank you. Assuming you can all hear me, just wait for my slides to show up. There we go. So hi, my name is Jasmin. I'm a research associate at Sustainable Gas Institute at Imperial. And in this presentation, I'm going to go over some of the work that we've been doing to estimate emissions across global gas supply chains, as well as looking at the methodologies used in national reporting. Just for a heads up, our work is entirely desk-based, so there'll be no nice pictures or fancy videos or movies. But there will be lots of graphs. So I'll start by just briefly going over the trends in the oil and gas sector's methane emissions before going over the work that we've been doing, and I'll finish with the main conclusions of the work that we've found. So as this will not be a surprise to anyone in this room, so methane emissions in the oil and gas sector have been increasing. There was a drop in 2020 because of the COVID pandemic, but it's expected that the results for 2021, when they get published, that they would have increased, and they're expected to be higher than they were in 2019. So within oil and gas methane emissions, there's a lot of uncertainty in what the emissions are, where they're occurring, and that's because of all the various reasons that everyone in this room, I'm pretty sure, knows. One area where there is a high degree of uncertainty is how much methane is emitted across individual gas supply chains. And that's something that we've tried to answer in a recent paper. I say recent paper. It got published last year, so I guess that counts as recent. So in this work, we estimated emissions for the world's largest gas supply chains. So taking into account the largest natural gas producers, consumers, and exporters and importers of LNG and pipeline gas. So 17 countries, which account for between 2/3 and 3/4 of global gas production, consumption, and trade. So for these countries, we estimated their emissions and also taking into account the emissions of the countries that import or export gas to these countries. So in total, we considered 80 countries and 252 gas supply chains, which included domestic production, consumption, pipeline, and LNG trades. And we estimated these emissions based on emission factor data provided in national inventories that are submitted to the UNFCCC. And we estimated the emissions for the year 2017. So in the emissions data that we collected, so in submissions to the UNFCCC, countries, they estimate their emissions using one of three methods, so tiers 1, 2, and 3. Tier 1 is when you estimate your emissions using generic emission factors. So these are emission factors that have been developed by the IPCC, and they're very generic. There are two sets. One is for developing economies and economies in transition, and the other set is for developed economies. Tier 2 and 3, they're higher level, and they will involve the use of actual measurement data towards estimating the emissions. So as you can see, in the data that we collected, there's a really big dependence on tier 1. So that means that for a lot of countries, they just don't know what their emissions are, so they have to use a tier 1. But using the data that we did collect, there we go. We estimated the emissions intensities across the different gas supply chains, and we found that there was a very big variation across supply chains. And the most important factor that impacted the emissions intensity was the methodology used to estimate your emissions. So for countries that use Tier 1, so for example, Iran, Malaysia, Egypt, their emissions were estimated to be higher. And that's because the Tier 1 emission factors, because they're quite generic, they're much more conservative, so they tend to be higher than the emissions you would estimate if you were to use Tier 2 and 3, which is why USA, UK, Norway, the emissions are much lower. So from going from the emissions intensity into quantifying how much methane is emitted. Nope, back. There we go. When you go from emissions intensity into kilotons of methane emitted, high emissions don't necessarily correlate to high volume of methane being emitted, and that's because when you want to quantify how much methane is being emitted, it's the throughput. That's the most important factor, which is why the USA and Russia, these two are the highest emitting supply chains, and that's because their throughput of gas is just much larger than the other countries and supply chains. So despite these two supply chains having emissions intensity that's about average or below average, because their gas throughput is so much larger than everyone else, the amount of methane being emitted is much larger. Something that was interesting in our analysis was when we looked at different import and export routes. So the country of origin does play an important factor. So if we consider pipeline imports to Italy and compare them with pipeline imports to Germany, you can see that Italy has much higher emissions. And that's in spite of Germany being the world's largest importer of pipeline gas. And that's because Italy, they get a significant portion of their gas from North Africa, where Tier 1 is used to estimate their emissions, whereas in Germany, all the gas comes from within Europe, where you use Tier 2 and 3 more often. So that does translate into Italy having higher emissions associated with their pipeline imports. Because of the high reliance on the Tier 1 in the data that we collected, we did an uncertainty analysis to see the impact that this would have on the emissions. So we conducted bootstrapping resampling and omitted the Tier 1 data and resampled our data set. And when we conducted this, we found that there was a significant reduction in the emissions. We found that in the upstream, there was a 3.8-fold reduction in the emissions and a 47% reduction in the downstream emissions. The upstream sees a much bigger drop in emissions, and that's because the countries that produce gas, it's a bigger proportion of them use Tier 1, whereas in the downstream, more countries use Tiers 2 and 3, so they were slightly less impacted when we did our resampling. And finally, moving on to a new piece of work that we've just recently started. So we're looking into the emissions methodology approaches used by different countries in the EU. So when we were looking into this to try to compare whether or not the new regulations specified in the new EU regulation for methane, whether more or less they're fit for purpose and how effective they could be in cutting emissions and what kind of cuts they could achieve. So when we were assessing the most recent submissions to the UNFCCC, so the 2021 submissions, so these would be the emissions reported for 2019, we found that even in the EU, there's still a very big reliance on Tier 1, with some countries not having any data on what their emissions are, so relying on Tier 1. And for quite a few countries, even though they will have measurement-based data on what their emissions are, they still rely on Tier 1 for some aspects of their emissions. For example, which one? Not that one. Let's see. So for example, Austria, they do produce gas, but very small quantities. But because the quantity is so low, they just assume Tier 1 emission factors, but they do apply Tier 2 to their downstream emissions. So brings me to my last slide. So in conclusion, we have estimated the emissions across the world's larger gas supply chains and found that there is a very big variation in the emissions. In terms of the emissions intensity, the methodology applied does have a very significant impact, with the countries that assume tier 1 having much higher emissions than those that assume tiers 2 and 3. And when we looked at the methodology used in reporting emissions in the different EU member states, we did find that even in the EU, there's still a big dependence on tier 1. And I'd like to thank the organisations that provide funding to the SGI. It's greatly appreciated. So my references, that is the paper that we published. And yes, that's it for me. Thank you.
Okay, so I will ask now the 4 panelists to come here just for the questions. So in case you have any questions, so please raise your hand. There have been very, very great presentations, so for sure you have questions to ask.
Hi, really enjoyed all the presentations. Thanks so much. I have a really simple question. So I'm new to the methane industry. I come from the carbon offset industry, and we're now looking at plugging oil and gas leaks. So my question is, just for a baseline to go out and ascertain whether we should buy an asset, what is a simple detection equipment that we could use for just like first line of defense to assess if there's methane leakage?
You want to take that?
I think you should take it.
So we, when we look at specifically just wells, we use a FLIR camera and we use a high flow sampler. So when we do see a leak, we can actually measure and quantify that leak. And then you can tell how much methane is associated with that particular leak. And that's a good correlation back to the carbon dioxide equivalent of that emission that you would be capping.
I would add that if you're looking for, if your business model is to cap wells to produce credits, and the question is, how can I find the most significantly emitting wells so that I can focus on those first? Aircraft tend to be a really great option for that. And so virtually any of the aircraft that we've talked about today could give you a really fast flyover and help you discern which of those wells were worth detailed measurements and P&A.
Cheers. Question for Jasmin, really. I'm just wondering, with the way the accounting is done from Tier 1, how much danger is there as people move from Tier 1 to other tiers is that reductions will be seen on a spreadsheet but not in reality?
That's a really good question. Quite high, unfortunately, because based on the historic data, we can measure more accurately what emissions there will be in present or in the future, but we can't do it we can't like trace back to what emissions were in the past. So just going off of what's been used and what is reported, we will have to use the Tier 1 emission factor data. So it's very likely that based on what is reported, there will be a really big reduction.
Maybe I can add that I think it's really important that this is also really monitored when this happens. Because, you read it then in the reports that the emissions have been reduced, and people, when you read it, they tend to believe it. I think it's really important that also at EU level, we don't fool ourselves by providing more detailed information, which on paper leads to lower emission rates.
Yeah.
So that's really important.
No.
Thank you so much for the presentation. I have a question which connects the presentation from Thomas and Jasmin. So in the presentation from Thomas, it was mentioned that the emission rate is kind of dependent from production. And in your presentation, you showed that in 2020, the emission was dropped. So it means that there is a connection, and emission is not dependent from production. So which one is true?
Contiguous?
Well, I think it's still an open question. I think on the site level, we see, and many studies have shown that there's not such a great correlation between production rate and leak rate. For the upscaling, this is still the thing that people use, because if you don't have more information about all the individual parts where you have not been, this is the only thing you can do. You can do for this area, maybe here I have a certain production rate, I've measured that kind of a leak rate here, and then I have a similar area where we have also not gone, then you would scale it up with the production. I think it's, well, you can do it on the site level, or fraction of site level, for example. But this is still something where I think in the upscaling, there's also a knowledge gap still. What is really the quantity that we can use best for upscaling? And it's not a trivial, it seems like a very trivial thing, but it's not so trivial.
Yeah, and just to add on, so the graph that I showed, that's the IEA's estimates. So, like, I believe in 2020, like, the drop in emissions was largely due to just the drop in demand in energy overall. So that the graph was actually in oil and gas methane emissions. So I think the largest contribution to that drop was actually the reduction in oil, because there was less road transport. We can't hear you.
Does that work?
Yes.
Yes. I want to offer a potential answer as well.
Okay.
So I think in Thomas' example, the differences in production didn't really correlate to differences in emissions, because you're looking at the same time frame. Whereas I think what we were looking at in Jasmin's talk, you have a time series of emissions, right? And so when in 2020 or 2021, when the emissions dropped, it was because some wells actually, they didn't produce, like the pump jack didn't go a little lower, like some wells don't produce for a certain time, right? And as a result, then you have lower emissions. So it's very different mechanisms of why production and emissions correlate or not.
Yeah, that would be a clear mechanism, right? If a well stops, it may still emit something, but it will be certainly less than when it's operating and it's leaking.
Yeah.
Is there any additional question? Okay, I don't see additional hands raised. So I really ask you for a huge applause for the great panelists. So thank you very much.